Hello everyone, I'm Krishna Lambichane. You can call me as a Krishna, your Physics 121 instructor for summer 2021. So let us start chapter 16. Chapter 16 is about electrostatics. So in this chapter we study about the electrostatics. Electrostatics, this is the study of charge at rest. So charge, there are two types of charge. One is proton. This is positively charged. And another one is electron. This is negatively charged. And if you draw the atom, look at this. This is the nucleus, the central portion of an atom. Here you have a proton. Proton simply you can write down P plus. And there is neutron also. Neutron you can write down N0. And electron is moving in a circular path like this. And this is called as the orbit, and electron is here. This is electron E minus. So I told you that the proton is positively charged, electron is negatively charged, and there is another particle, neutron. Neutron is neutral. Neutron, it is simply neutral, no charge. And in this case particularly, if you have one electron and one proton only, then in this case there is no neutron, because this is hydrogen atom. Hydrogen. In hydrogen atom there is no neutron, and this is the lightest atom, no neutron. Okay, so the proton P plus, one proton, one electron, and the charge in proton is 1.6 times 10 to the power negative 19 coulomb. The unit of charge is coulomb. So charge in proton is 1.6 times 10 to the power negative 19 coulomb, and you can take this positive in proton. And in electron, the charge here is again same, 1.6 times 10 to the power negative 19 coulomb here also. But this is negative. Negative 1.6 times 10 to the power negative 19 coulomb. This is charge in electron, and this is plus 1.6 times 10 to the power negative 19 coulomb in proton. So look here, one proton, one electron. 1.6 times 10 to the power negative 19 coulomb positive, 1.6 times 10 to the power negative 19 coulomb negative. This is negative, this is positive. They cancel out. That is why the atom is electrically neutral. Number of proton is equal to number of electron. Proton is positively charged, electron is negatively charged. Therefore, the atom is electrically neutral, because the positive charge and negative charge, they cancel out. Okay. So we are talking about the charge. Let us discuss little bit more about the property of charge. Like charge repel, and unlike charge attract. Like charge repel, proton and proton they repel, electron and electron they repel, but proton and electron they attract. Therefore, the similar charge, like charges, they repel, and unlike charge they attract to each other. Okay. And the second property is charge is conserved. Charge is conserved. You cannot create the charge. You cannot destroy the charge. The charge is constant, conserved. Like, if you rub the plastic ruler with a paper towel, if you rub the plastic ruler with paper towel, And you know that the plastic ruler is negatively charged and the paper towel is positively charged. Here look at this. Let us suppose this is a plastic ruler. If you rub this plastic ruler with, let's say this is a paper towel. If you rub this plastic ruler with paper towel, then paper towel becomes positively charged. And it becomes negatively, ruler becomes negatively charged. What does this mean? Do you create the charge? No. What happens is, if you rub the ruler with the paper towel donates some electron to the ruler. So there is an excess of electron here. Certain number of electrons transfer from paper towel to the ruler. That's why there is excess of electron. Number of electron is more than number of proton here. That is why this is negatively charged. And the paper towel, it is positively charged because it already donated the certain number of electron to the plastic ruler. So there is deficiency of electron here, or there is excess of like proton. The number of proton here is more than number of electron. That's why the paper towel becomes positively charged. The plastic ruler becomes negatively charged. So simply the charge, the electron transfer from paper towel to the plastic ruler. This is not creation. You can say transfer the charge from one object to another object. As a whole, if you count the total charge is always constant, always conserved. We cannot create, we cannot destroy the charge. It is conserved, it is constant. So this is the second property. And third property is, you can say the charge is quantized. Charge is quantized. What does this mean? What is quantization means? You can say the charge is quantized. What does this mean? This means, look here, the smallest unit of charge is, you can write down like this, E. This is equal to 1.6 times 10 to the power negative 19 coulomb. Again, the coulomb is the unit of charge. You can write down C to represent the coulomb. The smallest unit of charge is 1.6 times 10 to the power negative 19 coulomb. You do not have the charge smaller than this. Okay, so this is a charge in electron, or you can say this is charge in proton also, because the charge in electron and proton, they are equal, but they are opposite, you know that. Okay, so this is the smallest unit of charge. Now, in any object, if you have to calculate the, measure the charge, like in any object, you can write down the charge like this, N times E. Now this N is 1 times E, 2 times E, 3 times E, 4 times E, 5 times E, like this. You cannot take 1.1 here. No, that is not possible. You cannot take 2.5, 2.3, 2.7, 3.5. You cannot do that. Either 1, 2, 3, 4, 5. So integral multiple of this, 1.6 times 10 to the power negative 19 coulomb. This is what we call the quantization, quantized. Okay, so the charge is quantized. This is the third property of charge. Okay, now let us talk about there are two things. One is conduction, and there is another term we call electrostatic induction. What are these? What is conduction? What is electrostatic induction? Conduction is very simple. For example, let us suppose this is a sphere, one sphere, metal sphere, and here you have another metal sphere. Suppose this is positively charged. This is positively charged, like this, and this is neutral. In the beginning, initially, this is sphere, you can call sphere A is positively charged, sphere B is neutral. Okay, and by using, do you know the nail? Let us suppose this is nail, iron nail. This is iron nail. Okay. So this is iron nail. So if you connect the sphere A and sphere B by the iron nail, iron is the conductor. Iron can conduct the electricity. So it is a conductor. So what happened? The certain amount of positive charge transfer to this then this also becomes positively charged. So the charge transfer by touching, you use the iron nail. Using this iron nail, you connect these two spheres. So this is conduction. This is a conduction by touching. Okay. Now there is another one, electrostatic induction. What is this? Okay. Let us suppose you have a metal rod. This is the metal rod. This is the metal rod. And this metal rod is positively charged. Plus means it is positively charged. And you bring another metal rod. This is the metal rod. But this in the beginning, forget about this rod. Okay. You have a neutral rod. This is a neutral rod. And this rod, you bring this rod, and this rod is positively charged. You bring this positively charged rod close to the neutral rod. Now what happened here is negative charge developed here. If this is positively charged, the closer end right here, negative charge developed and positive charge developed there. So you produce the charge without touching. Okay. So the production of charge without touching is called electrostatic induction. The production of charge without touching, that is called as the electrostatic induction. Now here I use this word production, but few minutes ago I told you that charge you cannot produce, you cannot create the charge because charge is constant. So the production of charge without touching is called electrostatic. And what is this production means? Actually I am not producing any charge here. I use this word, that is okay, but I am not producing. What happened is I separate the charge only. You can use that word production, but we simply separate the charge. Using this charge, positive charge, what happens when you bring this positively charged rod close to the neutral rod? This is positively charged. So this positive charge attract the negative charge. So the negative charge come closer to the positive charge. I told you, unlike charge they attract. So this positively charged attract the negative charge. That's why the negative charge, that is electron, come closer to this positive charge. Of course, then this end becomes positively charged. So you simply separate the charge. We do not create the charge here, but still I use the word production. We can do that. Okay. So the production of charge without touching, this is called as the electrostatic induction. This is, we can call this charge, we call inducing charge, and this is, these two charge we call induced charge. Actually this inducing charge is equal to the magnitude, this charge is equal to this charge. Okay, and this also this one. This charge, inducing charge is equal to induced, this is we call bound charge. This charge is called as the bound charge because there is a strong force between them, and this charge we call free charge. So inducing charge is equal to induced bound charge, which is also equal to induced free charge. Okay, so this is the electrostatic induction. Let me give you another example. Let us suppose you have a sphere, metal sphere. Okay, this is a metal sphere, and this is a positively charged. This is positively charged metal sphere. If you bring another sphere, neutral sphere, close to this positively charged metal sphere, what happens? Can you complete the diagram? This is positively charged. Now you bring the neutral sphere close to the positively charged sphere. What happens? You don't touch. If you touch, of course, this becomes positively charged, conduction, but they are not in contact. You bring the neutral sphere close to the positively charged sphere. In this case, what happens is this end becomes negatively charged. This is negatively charged, and this end becomes positively charged. This end becomes positively charged. Okay, so this is the electrostatic induction. If you connect this to the ground, what happens then? This is we call earthing. If you connect this end close to the earthing, grounding. So what happens in this case? This proton goes to the ground, and look here. First, keep this positively charged sphere here and connect this sphere to the ground. This positively charged, positive charge proton, it goes to the ground, and remove this. Disconnect this, and remove this. What happens? This negative charge distribute in the sphere like this. Then the sphere becomes negative charge only. Again, if you want to charge this sphere negatively, what you have to do? First, you need a positively charged sphere. Bring this sphere close to the positively charged sphere. So this end becomes negative charge, this end becomes positive charge. Now keep this sphere here and connect this to the ground. So the positive charge goes to the ground. Now disconnect this, remove this sphere. Then this negative charge distribute on the sphere, and the sphere becomes negatively charged. Now here you should know one thing. Actually the electron is moving. Electron is moving in the circular path, we call that orbit. The proton is inside the nucleus. In fact, the proton is not moving, electron is moving. And here I told you that the proton goes to the ground. Actually that is not true. We can use that word, but actually what happened is ground has enormous amount of electrons. So what happened? The electron from here, from the ground, electron go from ground to there and neutralize the proton. You understand me? If you connect this into the ground, actually the negative electron goes there and neutralize the positive charge. That's what happened. That's what happened here. Okay, because the proton is inside the nucleus and the proton is not moving, only the electron is moving. So it is better to know. So this is about the electrostatic induction, and here I talk about the positive charge, I talk about the negative charge. So how do you detect the nature of the charge? You have a device you call electroscope. This is device to detect the nature of charge. Okay, or you can say that simply if you want to check the presence of charge also, you can use the electroscope. So electroscope, you can use this to detect the presence of charge or to detect the nature of the charge also. How is this? How is the structure of the electroscope? So the electroscope is, you have a one, this is a metal knob, and here of course this is a wire, and there is, this is gold, these two gold leaf. Gold leaf electroscope. Okay, so metal knob, and you have a gold, these are the leaf gold leaf. So we call the gold leaf electroscope. So these are these two, these and these, they are gold leaf leaves. Okay, So you can say gold leaf electroscope. Now what happened? How do you detect the nature of the charge then? For example, first you have to give the charge to this knob. So if this is negative, and if this is negative, this is a wire conductor, so this is also negative. So what happened? What happened here? Negative, the leaves, they diverge, repel, they diverge here. Now you have to detect the charge. So let us suppose this rod. If this rod is neutral, nothing happened. If this rod is neutral, nothing happened. Okay. Then what happened is here is if this rod is negatively charged, negatively charged, this negative charge repel this negative charge, right? This negative charge repel this negative. So if this negative charge repel, they go to there. So the repulsion increase. This goes like this, for the repel, right? If this is positive charge, what happened then? This positive charge attract this. So this goes there. So the amount of charge is decreased there. So they collapse like this. They come closer because the force is decreased here. Okay. So this is how it works. So simply, you don't have to, go in detail here. Simply the electroscope is the device to detect the presence of charge, to detect the nature of charge. Sometimes people, they can ask you what is electroscope. Okay, so it is the device to detect the nature of the charge, to detect the presence of the charge. That's what we call the electroscope. Okay, and it is simply based on the electrostatic, induction. So simply here you have to give the charge here. Using some source, you have to give negative charge or you have to give positive charge, it depends. Okay, and due to this charge, of course this also change here. So simply, if you want to detect the nature of the charge, bring the charge object here. If it is positive, then this come closer, collapse, and if it is negative, they diverge more. That is how you determine. Okay, so this is about the electrostatic induction. Okay, here I talk about the repulsion and attraction. So there is a repulsion, attraction, that's the force. Okay, and that's the force between two charged particles. You can have an attractive force, you can have a repulsive force, both. Attractive force, repulsive force. It is not similar to the gravitational force. You did that in physics 120. Gravitational force. The gravitational force is always attractive. But here, the force between two charged particles. Let us suppose this is one particle Q1, charged particle Q1, and there is another charged particle Q2. They are at a certain distance d. Here Q1 and Q2, they are charged particles. In mechanics, you did this. Let us suppose you have one mass m1 and another mass m2 here, and they are at a distance d apart. And there is an attractive force, and that force is called as the gravitational force, and that gravitational force F of g is directly proportional to the product of their masses m1 times m2 and inversely proportional to the square of the distance between them. This is the gravitational force. This gravitational force F of g equal gravitational constant, universal gravitational constant times m1 times m2 divided by d square. This is Newton's law of gravitational force. So the gravitational force is always attractive. And what is this? This is uppercase G. Always use uppercase G. And this uppercase G is 6.67 times 10 to the power negative 11 Newton meter square per kg square. A small number. Gravitational constant. Now here, you have a charge Q1, charge particle Q1, and you have a charge particle Q2. If this is positive, then there is a repulsive force. If this is positive and this is negative, I mean if this is proton and this is electron, then there is an attractive force. Like charge repel, unlike charge attract. So if this is positive repel. This is negative repel. This is positive, this is negative, or this is positive, this is negative. Unlike, they attract. So there is a force between two charged particles. There is a force between two charged particles, and that force is called as the electrostatic force, or you can call Coulomb force also. The force between two charged particles, that is called as the electrostatic force or Coulomb force. And the Coulomb force is attractive as well as repulsive. It depends on the nature of the charged particles. Okay, so there is a Coulomb's law. Coulomb's law. What is Coulomb's law then? The electrostatic force, look at this. The electrostatics, or you can say Coulomb force also. The electrostatic or Coulomb, the electrostatic force or Coulomb force between two charged particles is directly proportional the electrostatic force between two charged particles is directly proportional to the product of their charges and inversely proportional to the square of the distance between them, square of the distance between them. Kind of similar to this. Look at this, the gravitational force. The gravitational force is directly proportional to the product of their masses, m1 times m2, and inversely proportional to the square of the distance between them, inverse square law. Okay, here the electrostatic force is directly proportional to the product of their charges. Here product of the masses, here product of the charges, and inversely proportional to the square of the distance. Here same thing, here inversely proportional to the square of the distance. So there is a similarity, okay, between these two forces, Coulomb force and gravitational force. Okay. So you can write down the Coulomb force. You can use F of C. It is a Coulomb force, or you can write down, let me use F of E, electrostatic force. I think that is better. F of C, sometimes you confuse. F of C is centripetal force also. Coulomb force can also act as a centripetal force. You know that. You learn that in chapter 5. Okay, the electrostatic force, or you can write down Coulomb force, F of C. This is proportional to the product of their charges, Q1 times Q2, and inversely proportional to the square of the distance between them. Therefore, the electrostatic force, F of E, or you can write down F of C also, is directly proportional to the product of their charges, charge particle Q1 times Q2, and inversely proportional to the square of the distance between them. This is the Coulomb's law of electrostatic force. And please note, the electrostatic force is attractive as well as repulsive. But this one, this F of E equal, you can write down K Q1 Q2 divided by D square. This gives you the magnitude only. Okay, the magnitude of electrostatic force. This formula gives you the magnitude of electrostatic force. And here K is lowercase k. This K is, you can write down 9 times 10 to the power 9. It is actually 8.99 times 10 to the power 9, but roughly you can write down 9 times 10 to the power 9 Newton meter square per Coulomb square. And this is called as it is proportionality constant. Look here, I have the proportionality sign. I want to put equal sign here, so I put this constant we call Coulomb constant. It is proportionality constant, and this is called as the Coulomb constant. Coulomb constant. Okay, so the Coulomb constant, I strongly recommend you guys, please memorize this number, 9 times 10 to the power 9 Newton meter square per Coulomb square. So this is the Coulomb's law, okay, of electrostatic force. F of E is equal to K times Q1 Q2 divided by D square. This is a Coulomb's law. Okay, so this gives you the magnitude of the Coulomb force or electrostatic force. Now you can think about this formula. Look, Q1 Q2. So if you double one charge, what happens? Let us suppose initially this is 1 coulomb, this is 1 coulomb. Now you double the one. You make this charge is 2 coulomb, another one is 1 coulomb. If you double one charge, your electrostatic force is simply double. If you double both charge, in that case it is quadruple, then the force is quadruple. Now if you double the distance, you make it 2d. What happens in that case? You have to write down 2d square. So 2 square 4. So it is 1/4. If you double the distance, your new force is 1/4 times the original one. If you double the distance. If you cut the distance into half, what happens in that case? Look at this. If you cut the distance into half, what happens in that case? Look, initially you have F E equal to K Q1 Q2 divided by D square initially. Now if you make it D divided by 2, cut the distance into half, this means F E, let me write down F E prime, new force is K Q1 Q2, you cut the distance into half, that means D divided by 2 into half, so, and you have to square this. So what is this equal? This is Fe prime, this is 4 times K Q1 Q2 divided by D square. So this is 4 times Fe. So therefore, if you cut the distance into half, the force is again quadruple. So please play with this formula. K times Q1 Q2 divided by D square. This gives you the magnitude of the force. Coulomb force. Okay. Now think about this. You can try this yourself, everyone. Let us talk about the hydrogen atom. This is hydrogen atom. Here you have a 1 proton and there you have 1 electron and proton, and the distance between them is simply you can call radius of the hydrogen atom. This is hydrogen atom. It is a spherical, I mean you draw it like circular, okay? Yeah. So the distance between the proton and electron is radius of the hydrogen atom. And you know that mass of proton is 1.67 times 10 to the power negative 27 kg. Mass of electron is 9.1 times 10 to the power negative 31 kg. Okay, so the distance between the proton and electron is r. R is distance between proton and electron. Here I'm talking about the hydrogen atom. Okay, hydrogen atom. R is the distance between the proton and the electron. Make this is kind of this is really funny. Make it a little bit circular. Okay, this is a circular. Make a circular one. Okay, so R is the distance between the proton and electron. So you can calculate the gravitational force. What is your gravitational force? F of G equal to G mp, mass of proton, mass of electron, divide this by r square. Calculate this, you figure out the r, okay, the radius of the hydrogen atom. You can do the Google search or you can look at the textbook. I think it is 0.53 times 10 to the power negative 10 meters. But please check that, okay, 0.53 times 10 to the power negative 10 meter, that is r. But please check the number, okay. So this is a gravitational force. And how do you calculate the electrostatic force? To calculate the electrostatic force, you need the charge in proton, QP, charge in proton, that is 1.6 times 10 to the power negative 19 coulomb. Electron is again same, negative 1.6, magnitude is same 19 coulomb. And of course you can use the formula, electrostatic force F of E equal to K QP times QE divided by R square. R is same, okay, R is same. And K here is 9 times 10 to the power 9 Newton meter square per coulomb square. Gravitational constant here is 6.67 times 10 to the power negative 11 Newton meter square per kg square. So please calculate this, and calculate this. Then compare which is big. Please do this. This is homework for you guys. Okay, this is not difficult job. The only thing you have to figure out is what is R. R you can check your textbook. I already mentioned it is 0.53 times 10 to the power negative 10 meter. I think I am right, but please make sure that is correct. Okay, then calculate the gravitational force, calculate the electrostatic force, and then you can compare. Definitely you get this force big. How many times? Way bigger than gravitational force. Please do that. I think it is about 10 to the power 39 or 10 to the power 40 times bigger. Electrostatic force is really very big. The reason is gravitational constant. This is 6.67 times 10 to the power negative 11 Newton meter square per kg square, 10 to the power negative 11. But here K is 9 times 10 to the power positive 9 Newton meter square per coulomb square. This number is big. That is why the electrostatic force is bigger. So please do this. It is good practice. Okay. So the coulomb force, the formula, you have a formula there that gives you the magnitude. So look at this again. F of E. This is K Q1 Q2 divided by D square. This is the formula. This formula gives you the magnitude of the force between two charged particles. But you know that the force, it is the vector quantity. So if it is the vector quantity, then you must give the direction of the force then. Let us suppose this is one charge Q1 and this is another charge Q2. So there is a force between these two charged particles. How do you figure out the direction of the force then? So the line joining them, this line join these two charged particles, like the line joining them gives the direction of the electrostatic force. The line joining the charges. Charges gives the direction of electrostatic force. But how do you get the direction then? I said the line join the straight line joining them, that gives you the direction of the force. How? Look at this. Okay, it depends. Let us suppose this is positive and this is also positive. Same charge, like charge, they repel. So how do you get the direction then? Join these, draw the line, straight line, join these two charges, and this and this, they repel. Repulsion, move away, right? If this is negative, this is also negative, same thing. Repel. But if this is positive and this is negative, again draw like this. So this way, this charge attracted by the negative charge, and this negative charge is also attracted by the positive charge, like this. They attract to each other. Unlike charge, they attract. Like charge, they repel. If this is same thing, if this is negative, this is positive. Same thing, you draw the line like this, then you can draw this and this. You understand me? So if you have a like charge, they repel. If you have unlike charge, they attract. So the direction is you draw the line, straight line, join the two charges, drawing the straight line, and that gives you the direction like this. Sometimes like you can think about this. Let us suppose you have an equilateral triangle like this. This is equilateral triangle. And you keep 1 microcoulomb charge here. 1 mu means microcoulomb. Okay. And here also you have a 1 microcoulomb charge there. And here also this is also 1 positive 1 microcoulomb. Microcoulomb, you have to convert this. 1 microcoulomb is 1 times 10 to the power negative 6 coulomb. You have to convert this into coulomb. There is another one millicoulomb also. If you have 1 millicoulomb, this is 1 times 10 to the power negative 3 coulomb. Okay. So here I have an equilateral triangle. Let us suppose the distance between like here, and this is equilateral triangle. So whatever, let's say 5 centimeter, 5 centimeter, 5 centimeter, 5 centimeter. You have to convert centimeter into meter. Okay. These numbers I randomly chose the number here, so I don't know if it makes practical sense. But I have an equilateral triangle. The side of the equilateral triangle is 5 centimeter. Equilateral means equal sides and equal angle also. Now what is the net force here? You have 3 charges. You have a Q1, you can call this is Q1, this is Q2, and this is here you have a Q3. So how do you calculate the net force? Right here you can, it is identical, so right there, right here. So how do you calculate the net force here? Numerical power. So the force experienced by this charge is because this charge repels this charge. So the force right here due to Q1 is this force. It is this way. You join the line. This is the line joining these two charges, and this is the same charge, positive and positive. So what happens? Repel. So it goes this way. Now the force due to this charge Q2 here, you can call this is, let's say, F. You can call FA whatever, okay. And the force due to this charge Q2 charge is, you can write down like this. This is, you can call FB. So this is a force due to Q2 and this is a force due to Q1. So how do you get the net force then? You have two vector FA and FB there. So how do you get the net force then? The net force is, look, this is one side of the parallelogram and this is another side of the parallelogram. Then you can complete the parallelogram like this, and this diagonal, this one, this is your resultant f of r. This is a vector, this is a vector, this is a vector. So your f of r, this is the resultant force at this point. This is equal to f of A plus f of B. This is how you have to write down. But the concern here is the resultant force. It is a vector quantity. So simply you cannot add them. You have to apply the vector law. Okay. So f of A, this is a vector, and f of B, this is also vector. But vectorially we write down like this. This is the resultant force. So how do we get the magnitude? We'll do the problem, okay, in a class. Numerical problem. So you have to do it vectorially because the force, Coulomb force, or whatever force is always the vector quantity. You have to give the direction. So if you have to calculate the magnitude only, that is also sometimes difficult. Okay. So you have to give the magnitude and the direction. So to calculate the magnitude, in this case, this is one particular example. There are many different types of problem, So this is one very common, and it takes a little time also. This is a little bit long problem, but of course we'll do the numerical problem in our discussion section, okay, in a class. Okay, so this is about the electrostatic force, okay, we also call Coulomb force. So Coulomb's law, that is this, the Coulomb's law is this: electrostatic force is equal to K times Q1 Q2 divided by T square. But this K you can also write down like this: K equal to 1 divided by 4 pi. You can write down this is epsilon 0. K is equal to 1 over 4 pi epsilon 0. Epsilon 0 we call this is permittivity of the free space. This is permittivity of the free space, or you can say here also. What is permittivity? What does this mean? This means the response of the free space to the charge. That is what we call the permittivity epsilon 0. Permittivity epsilon 0. So this is epsilon 0. This is equal to, this is constant. This is, I think, 8.854 times 10 to the power negative 12. Okay, so this is, now what is the unit then? I think it is Coulomb square per Newton per meter. So this number, better to memorize this, or you can write down in your formula sheet. 8.854 times 10 to the power negative 12. You can think about the unit. I think I am right. Coulomb square divided by Newton per meter. Newton meter. Coulomb square per Newton meter. Please check this. Okay. Okay, so this is a Coulomb force, and next topic we have to discuss is electric field. Electric field. And electric field simply represented by E, and this is a vector quantity. Electric field, you use uppercase E, and electric field is a vector quantity. So any idea what is electric field? How do you define the electric field? Look here. Let us suppose this is the charge. We call charge, I can use uppercase Q, lowercase q, that is not a big deal. We call this is a charge. We can call this is the source charge. This is the source charge, a little bit big, okay? And of course, if you keep the charge, for example, think right here, you keep one charge right there, then you can experience the effect of that charge around here, this area. In the here you have a charge right there. Consider here you have a charge. You keep the charge here, and of course you can measure the effect of charge around here, electric field. Now, so in this area somewhere like this, you can feel the effect of this source charge, but you choose one point right here. Okay, the electric field, actually it is better to say electric field strength. The electric field strength is defined inside the electric field, where you can measure the effect of charge. So look at this area where you can feel the effect of this charge. Inside this area, okay, inside this whole area, I choose one point here. Let me call point P. Okay, because the electric field or electric field strength E, I'm talking about the E, the electric field. Actually, it is electric field is strength, but people they call electric field. The electric field is defined inside this area where you can feel the effect of charge. If there is no effect of charge, electric field is simply that is zero. Okay, so I choose this point, and this point is at a distance, let me call R, from the source charge. And the electric field at this point, to define the electric field, you have to right there you have to put one little charge Q0. We call test charge. This is tiny test charge, really tiny. This is tiny, very small charge. we also call unit positive test charge, or simply you can say the tiny charge. So the electric field at this point, I said the electric field is always defined inside the certain area there where you can feel the effect of charge. Okay, so the electric field at point P, E, this is equal to force, electrostatic force per unit test charge. This is what we call the electric field. So electric field is force, electrostatic force per unit test charge. That is what we call the electric field. So this is the definition. Okay, this is the definition. Now from here you can see that the electric field is, force is Newton, charge is Coulomb, Newton per Coulomb. That is the unit of electric field. Force per unit test charge, that is the electric field. Force experienced by the unit test charge also, that is the electric field. And the electric field is F of E divided by Q0, and F of E, this is the force Newton, divided by charge, charge is Coulomb. So Newton per Coulomb, that is the electric field. Newton per Coulomb, that is the electric field. So from here also, if you have to calculate the electrostatic force F of E, you can do this also. Q naught times electric field. This is another formula to calculate the electrostatic force. And here I use the Q0, tiny charge, small charge, but whatever charge you have, simply you can write down like this also. The electrostatic force is any charge work, Q times E. This work. So this is the formula to calculate the electrostatic force. Another formula. Okay. So now look at this. This is a definition, force per unit charge, that is a electric field, Newton per Coulomb. Again look here, let me rewrite, electric field E, this is equal to F of E divided by Q0. What is F of E here? Look, F of E is force between Q0 and Q, right? So if you write down F of E, you can use the Coulomb's law, K Coulomb constant, Q1 is uppercase Q, Q2 is Q0, divided by distance square, distance is R. So you have to write down R square. So plug this here, then your electric field E, this is equal to K Q0 divided by R square. This is your F of E. Divide this by Q0, right? So what happens? This Q0 and this Q0 cancel out. Therefore, the electric field E, this is equal to K Q divided by R square. KQ divided by R square. So this is the electric field. K Coulomb constant times source charge divided by distance square. So from here you see that the electric field right there or at any point, it depends on this charge, not the test charge. The electric field at any point, it depends on the source charge and the distance between the point and the source charge. It is independent of test charge. Look, there is no test charge here. You have a source charge and you have a R here, R square. So what does this mean? If you move away from the charge, your electric field is decreasing. If you go really very far, then it becomes zero then. If your R is increasing, electric field is decreasing. That means if you move away from the source charge, your electric field is decreasing. Okay, then you can think about the direction of the electric field. I told you that the electric field is a vector quantity. You must give the direction of the electric field then. So how do you figure out the direction of electric field? The electric field is, for example, look at this. This is your positive charge. Here you have a negative charge. The direction of electric field is always from positive to negative charge. The direction of electric field is always from positive to negative charge. For example, let us suppose you have a positive Q charge here and you have another charge. Let us suppose if this is a positive. If this is a positive. So what is the direction of electric field? Electric field is this direction. This is your electric field. What is the direction of the force here then? The force is also in the same direction. E, sorry, not E, F. If this is positive, both are positive. In this case, the electric field is away from the positive charge. This is also away from the positive charge. Force and electric field, they are in the same direction. In this case, if both are positive and positive. But what happens? What happens if you have, let's see, this is positive Q, and if you have a negative here, so in this case, electric field is in this direction, because electric field is always from positive to negative. This is electric field. This is the electric field. Okay. What about the electrostatic force then? This is negative charge. Okay. What about the electrostatic force? It is attractive. The electrostatic force is in this direction then. Okay. So the electric field vector quantity, the direction of electric field is always from positive charge to negative charge. Okay. And this formula, look here, summarized today, we did this F of E. This is a Coulomb force, is K Q1 Q2 divided by D square. This is a Coulomb's law, Coulomb force. And we also define the electric field E. This is equal to F of E divided by Q0. Okay, this is the electric field E. Or electric field E, you can also write down like this, K Q divided by R square. This is electric field at a point due to point charge. This one, this E. This is electric field at a point due to, we call point charge. Okay. So this charge, the source charge, it is a point charge. It's like the shape is like a point, little sphere. Point charge. If you have like let's say if you have something like a big sphere, this is a charged particle, then how do you calculate the electric field? Like you have like a basketball, and the basketball is, think about like the size of the basketball, and it is made of, let's say, copper, something like that. And if that is a charge, how do you calculate the electric field? That is a different story. We have to learn the Gauss law. That is my next lecture. Okay, so simply today we talk about the conduction. Is very simple. We talk about the conduction, we talk about the electrostatic induction, we talk about the charges and properties of the charges, and we talk about the Coulomb's law, electrostatic force, we talk about the electric field, and we write down the formula for the electric field due to the point charge. Okay, I think this is all for today. Then I'll bring another video. This chapter is not done yet. I have to talk about the electric field. Okay, I have more about the electric field. I have to talk about the Gauss law. Okay, thank you.